Let's jump right into today's explainer. We're taking a highly technical deep dive into the invisible, high-stakes architecture that actually keeps an electric vehicle safely moving down the road. Specifically, we're demystifying a really critical hardware and control failure, the high-voltage contactor stuck open fault. Now, this isn't just about some random part breaking. It's about what happens when the massive flow of power from the battery to the wheels is unexpectedly interrupted.
To really picture the role of this main contactor, I want you to imagine it as a massive high-voltage drawbridge. When you power on your car, this drawbridge absolutely must lower perfectly to let electricity flow across the moat, so to speak. But what happens when that 800-volt drawbridge flat-out refuses to lower? Or, man, even worse, imagine you're cruising at highway speeds and that bridge suddenly snaps back open. You'd experience a catastrophic sudden loss of propulsion right there on the highway.
Because the consequences of that sudden power loss are so incredibly severe, this specific failure mode operates under the shadow of ASIL D. That's Automotive Safety Integrity Level D, which is the absolute highest classification of initial hazard in the ISO 26262 safety standard. Look, this isn't a check engine light for a loose gas cap, right? This is a critical safety violation that demands literally flawless engineering. Lives quite literally depend on that contactor working perfectly every single time.
Okay, let's dive into this investigation. We'll be mapping this out across 5 key areas: failure, root cause, hardware and software diagnostics, DFMEA design defense, PFMEA factory controls, and wrapping up with DVPNR extreme validation.
Starting off with Section 1, Failure Root Cause. Let's investigate the actual physics of the fault.
We really need to treat this system failure with serious urgency, honestly, kind of like investigating a physical crime scene. A stuck-open contactor is usually the result of a microscopic chain reaction across one of 4 dimensions. First up, you've got coil thermal overload. If the low-voltage coil gets fed way too much power, joule heating melts the insulation, and that causes turn-to-turn shorts. Second dimension, driver semiconductor open failures. When a relay disconnects, it creates this massive reverse voltage spike that can actually fry the driver chips. Third is mechanical friction and icing. And finally, mirror contact signal false opens. That's where microscopic disconnects literally trick the car's computer into thinking the contactor is open, even when it isn't.
Now, a major catalyst for these physical failures actually happens between 100 and 1,000 Hertz. That range represents the high frequency of random vibrations your car dynamically experiences while you're just driving down the road. Over time, this constant rattling causes what engineers call fretting wear. Basically, microscopic metal shavings build up on the contactor's slide rails. Combine that metallic debris with, say, -40°C temperatures, where condensation can freeze into solid ice, the contactor's iron core can literally jam in place. The magnetic force simply cannot overcome that friction.
Moving to Section 2, Hardware and Software Diagnostics, and the System Security Protocols.
Knowing that raw physics can and will degrade the hardware, an ASIL D architecture has to be smart enough to detect these failures almost instantly, and by instantly I mean within a ridiculously strict 60 millisecond safety window. To put that in perspective, that's literally faster than the blink of an eye. This is pulled off by incredibly smart drivers constantly monitoring the system. In the off state, the chip injects a tiny microamp bias current. It's not enough to trigger the relay, but it is enough to check the circuit's impedance. If a wire is broken, it knows immediately. In the on state, it actively monitors the output current. If it detects a surge from a short circuit, boom, it autonomously shuts down the channel in less than 10 microseconds. On top of that, the main computer checks the mirror contact state just 20 milliseconds after a close command and verifies that the bus voltage is rising properly within 50 milliseconds.
But hold on, what if the main computer itself makes a mistake? Well, that brings us to the doer-checker architecture. Think of this exactly like a pilot and a co-pilot, both flying the plane with their hands on independent kill switches. The doer core executes the normal relay commands, meanwhile the checker safety core independently verifies the voltage, the current, and the contact state. If they ever disagree on what's happening, the checker cuts power within under 100 microseconds, locks in a P0A09 error code, and permanently forces a safe state to prevent any secondary, high-voltage arcing. It's an absolutely flawless system of checks and balances.
Next up, Section 3, DFMEA Design Defense, where we engineer the solution proactively.
Of course, it's always better to build preventative measures right into the circuitry from day one, a process known as DFMEA. This brilliantly illustrates one of my absolute favorite engineering solutions, the PWM economizer. Remember earlier how we said constant power melts the coils? Well, engineers use a great analogy for this. It's like sprinting to close a heavy door, but then just casually leaning on it to keep it shut. The system applies a 100% duty cycle for just 100 milliseconds to forcefully pull the contactor closed. But once it's closed, it drops the power to just a 20 or 30% high-frequency pulse. This clever trick slashes heat generation by over 70%, completely preventing thermal overload while maintaining a totally secure connection. They also pair this with dual-channel redundant topologies and high-temperature transient voltage suppression diodes to strictly clamp down on those destructive voltage spikes we talked about earlier.
Let's roll into Section 4, PFMEA Factory Controls, enforcing absolute perfection on the assembly line.
Now, what's really interesting here is that all this brilliant design work means absolutely nothing without flawless factory execution, and that's known as PFMEA. Just look at this incredibly strict threshold, 5%. When the driver circuit boards are soldered on the factory line, they pass through a 3D X-ray scanner. If the total volume of tiny air bubbles or voiding in the solder exceeds just 5%, the part is immediately scrapped. Actually, even a single isolated void larger than 1% is rejected. Why so strict? Because under the constant heating and cooling of a daily commute, a microscopic void can lead to a thermal crack. That crack leads to driver failure, which leads to the contactor getting stuck open. The factory enforces this level of perfection using 100% automated online testing, like LCR meters that scan the exact electrical resistance and inductance of every single coil before it's even assembled into the final unit.
Finally, Section 5, DVP&R Extreme Validation, which is the ultimate stress test.
Before a single vehicle ever reaches a customer, the system enters the final stage, extreme DVP&R validation. These parts are subjected to brutal, multi-physics compound stress tests far beyond normal earthly limits. I mean, they are strapped to a machine vibrating aggressively across 3 axes while simultaneously being blasted with temperatures ranging from -40 to 125 degrees Celsius for 1,000 continuous hours. It's wild. And look at the temperature limit test parameters here. At -40 degrees, the contactor must still forcefully pull in, even if the car's 12-volt battery drops below 9 volts. Conversely, at a blistering 125 degrees Celsius, it has to guarantee it can still cleanly drop out and disconnect power instantly in an emergency.
All of this rigorous testing builds to the absolute climax, the hardware in the loop, or HIL, dynamic fault injection. Picture this. Engineers strap the EV's motor to a dyno, spin it up to a screaming 12,000 RPMs under maximum load, and then they violently and intentionally inject a hardware fault, instantly disconnecting the low-voltage drive circuit. The result? The system successfully diagnoses the failure in less than 60 milliseconds. It smoothly commands a safe active open circuit state. The massive electrical phase current gracefully decays to 0 without any dangerous voltage spikes, and crucially, without any wheel-locking brake torque that would cause the driver to lose control of the vehicle.
Which brings us to a profound realization summarized perfectly right here. In the world of ASIL D, safety isn't guessed, it's simulated, tested, and guaranteed at the thermodynamic limit. To pull this off, engineering teams built complex transient Python models that couple electromechanics with thermodynamic equations just to calculate the exact margins of safety. It is an astonishing level of invisible precision. So the next time you silently accelerate onto a highway, ask yourself, how many thousands of microscopic, perfect decisions are happening right beneath your feet to safely keep that 800-volt drawbridge closed? It's pretty fascinating to think about. Thanks for exploring the depths of this complex system with me on today's Explainer. Keep learning, and I'll catch you next time.